Okay, so this is where we left off in class. So we've probably only got about another 5 or 10 minutes to finish this lecture. So I wanted to give it here rather than to try to drag you back into a synchronous meeting to get it done. So I'm just going to take the 5 or 10 minutes to go through that, record it, and leave it for you to get through. So we had just finished our free body diagram where we had taken a beam, done the free body diagram for it, and then resolved it to come up with our reactions at the supports. And so the next logical thing for us to discuss is whether our structure itself has adequate supports to carry the load. And one of the concepts that we need to understand is whether it is determinate, statically determinate, or indeterminate. And that really is it stable? And if it is stable, does it have excess supports that we can't resolve it using static equations, or simply resolve it using just static equations? So if something is statically determinate, we know that the number of unknown external reactions, so remember our supports, right? So roller support, 1 reaction, pin support, 2 reactions, 2 translation reactions, and fixed support, so our 2 translation reactions and our moment, so that's in 2 dimensions. So the number of unknown external reactions based on the types of supports we have is equal to the number of equations of statics. So in 2 dimensions, how many equations of statics do we have? We have some of the forces in the x direction equals 0, some of the forces in the y direction is equal to 0, and we have some of the moments must be equal to 0. So we have 3 equations. So we have to have a system where the number of reactions is also equal to 3. So that means it will be both stable and determinate, as in we can use our equations of static equilibrium to resolve it. So it is indeterminate if the number of unknown external reactions is greater than the number of equations. It's still stable, it's still adequate to carry the load, but it is more complicated to solve it, and we can't resolve it simply using the equations of static equilibrium, and it would become statically indeterminate. Something is unstable if the number of unknown external reactions is less than the number of equations of static equilibrium. So we haven't provided the structure adequate support to carry the loads, and it would be unstable, and that can be determined by the number of external reactions compared to the number of equations of static equilibrium. So here we just run through some quick examples. We'll go through them very quickly. So they're all in 2 dimensions, so the number of equations is always going to be equal to 3. And what we have to do is look at the number of unknowns, and those are unknown reactions at the supports. So we add that up based on the types of support. So a pin always gives us 2, and a roller always gives us 1, and a fixed support always gives us 3. So in this case, if we have 3 equations, we also have 3 unknowns. And this is a simply supported beam. It's a very classic style of beam support condition, and we use it fairly often. And so this is statically determinate, and we can resolve it using the equations of static equilibrium. So in this example, in the beam, of course, we have the same number of equations, and we have 2 unknowns from the pin support, and we don't have anything else, so we have 2 unknowns, and so this would be unstable. And it's pretty easy to look at the structure knowing that we have no moment resistance at a pin, and seeing that it is going to be unstable and is not able to carry the load in a condition where it's not going to move. So one more where we put our roller support at either end. Again, same number of equations. And if we look at our reactions, we have 1 for each of the rollers, or 2 equations. So this also would be unstable. We can see that by applying our force, this is unstable in the lateral direction and would roll away under load. So now we introduce our fixed end. Remember 3 equations, right? Our 2 translation equations, x and y, or reactions x and y, and our moment reaction about the support. So same number of equations. In this case, 1 fixed end gives us 3 unknowns, and so we have a determinate system. If we went with 2 pin ends, we would have our 3 equations, and we would have 4 unknowns. And so this is an example where it is stable, but it is indeterminate. We don't have enough equations of static equilibrium to resolve this problem directly. And we're going to see later on how we're going to deal with that. So it is indeterminate. And the same thing, this is a propped cantilever. So this cantilever was the first one here with the fixed end. So here we have the fixed end, but we have it propped up at the end with a roller support. So same number of equations. We have 3 unknowns due to the fixed end and 1 unknown due to the roller support. That gives us 4. It also is indeterminate. And so if a beam is fixed at both ends, so we have 3 equations, 6 unknowns. So again, it is indeterminate, but the degree of indeterminacy is just growing. So this is indeterminate to the 3rd degree. And again, in a continuous span beam situation where we have 3 pin ends, so that would be our 3 equations, again with 6 unknowns. And once again, we have an indeterminate structure. So statically determinate structures can be solved for all reactions using just the equations of static equilibrium alone. So in 2D structures, 3 equations, 3 unknowns. If that was in 3 dimensions, you end up with 3 moments and 3 translations, x, y, z, and moments about x, y, z. So you have 6 equations and 6 unknowns. So statically indeterminate structures then cannot be solved for all the reactions using just the equations of equilibrium by themselves, but they can be solved. What we need to do is we have to introduce an issue called compatibility, and basically we add another equation to make the system work, and that allows us to resolve it. And we're going to see how we're going to deal with that a little bit later on. So you need a compatibility equation for each degree of indeterminacy. So if something has 1 extra reaction, so say 4 reactions in 2 dimensions and 3 unknowns, or 3 equations, 4 unknowns, you would need 1 compatibility equation to resolve it. So now we have some class examples, and so this is the first class example. I walk it out fairly slow speed. This is the link that you can follow to get to it. Some of the things that I talked about during the lecture are reinforced with this, so this is really worth taking the 10 minutes, I think it is, that it takes to watch it. Watch it in slow speed, copy it out. Hopefully this is part of the review, so you're not learning a lot new, but I do put some emphasis on the note-taking and laying out the problem. So please have a look at that and see if we can't learn some good lessons right off the start. So once you're done that, there's the free body diagram done out so you can see it in detail. I'm going to talk a little bit about the types of loads. And now we talked abstractly about the types of loads on our little potato model earlier on. In our 2 dimensions, we'll see them here. So shown on a beam, our point load shown as a concentrated load or point load acting at a single point. It has a magnitude and obviously a direction, and it is represented in newtons or kilonewtons. A distributed load, remember that 2-dimensional distributed load, like a snow load or something like that. Snow load, when it's represented down to 2 dimensions, obviously it exists in 3 dimensions in the real world. And so a uniformly distributed load, which is to say that the magnitude is not changing over the length of the load. So in this case, represented by an intensity W, and that is given in newtons per meter or kilonewtons per meter. More commonly, and it is applied uniformly over the length. Now, the total load for the distributed load is, as we mentioned earlier, the area under the load curve, or the integral from one side to the other, which is your area under the curve. And so because this is a fairly straightforward shape, it's a rectangle, we have a height, which is our intensity W. We have a length, which is in this case the full length of the beam, or the length over which the load is applied. And so we can multiply the 2 together, W times L, and that is the equivalent point load acting through the center of gravity of the rectangle, which is in the middle, and shown here with a little squiggly through it because it is an equivalent point load for the uniformly distributed load. Great for resolving into reactions and things like that. Be careful when you're looking at internal forces, because if we're inside the area of application of the uniformly distributed load, we need to break that up into its bits. And so you can't just replace it with the equivalent point load. We'll talk more about that. Then we have a triangular distributed load. And so here we're going to get a load of a linear variability. So it's going to vary from 0 at one end to an intensity Q sub naught at the fat end or the blunt end. And so it forms the shape of a triangle. Triangular distributed load, again, kilonewtons per meter, but that is the intensity at the blunt end, obviously varying linearly down to 0 at the other end. Again, it can be replaced by a equivalent point load through its center of gravity. Its center of gravity for a triangle is 1/3 from the blunt end or 2/3 from the pointy end. And so we can see that here. And so it's 1/2 the height. So 1/2 times Q naught times the base, which is the length. And so that would be the magnitude of that equivalent point load. Once again, if you are actually looking at internal forces somewhere along the line of load application, you have to be very careful using just the equivalent point load. And again, we'll talk about that as we develop our skills in the problems moving forward. And we have our applied moments. So we can apply a moment anywhere. It has M. It is in units, newtons per meter or kilonewtons per meter. And it has an impact on the entire structure. And we can see it here when calculating reactions. The sum of the moment at any point must include the applied moment, and you don't have any length or distance associated with it. It is just the moment applied, period. So in this case, some of the moments about A as an example. So these two, because their perpendicular distance goes to 0, or their line of action is through the point of interest, they don't cause any moment. So we have three things causing a moment. We have P, our moment, and our RBY. So P times its perpendicular distance, which is L over 4, our RBY times its perpendicular distance of L, and no M gets added in, and there is no distance associated with it. It just gets added in directly. It's clockwise. We've said clockwise is positive, so it has a positive sign. So finally, we're closing out with some of the details, the sign conventions that we will typically use for this particular course. So for a couple things to understand, a sign convention is always arbitrary, and we can change it anytime we want, but we will try to use the same sign convention so that we can make sense of things. If we assume a direction when we're drawing something out, so we put in a reaction and we show that the reaction is up, for example, and if we get a negative answer, we know that the reaction is actually going in the other direction than the way we draw it. So we apply the sign convention as per the manner in which we drew it on our free body diagram. And then when we get to the result, if we have a negative answer, we're just going to have to reverse the direction of the arrow. So this provides consistency and prepares us for numerical applications, which have a very rigid sign convention so that the computers can interpret these calculations effectively. And keep in mind that some processes demand a very specific sign convention so that the process itself works. And more circles would be an example of that. I know you don't know what that process is. You'll get that. I'll allude to it during this course, but really it's in the third year course that you learn about more circles. So what do we use? What was our typical sign convention for this course? So normally tension is positive. So remember, a force or a stress acting on a structure can be in compression or in tension. So we use tension as positive and compression is negative. So you just kind of memorize that, remember it. I always think about, if something's in tension and you pull it and it pops the two arms up to make a plus sign, however you want to think of it. Tension is positive. Shear is positive if on a positive direction on a positive face. We're going to talk a lot more about that when we get into direct shear and everything else. But so this point, which is represented by this cube, exists at a point, and the positive face is the face that's on the positive side of the axis that it's on, or that it's perpendicular to. So this axis where V sub xy is shown is the positive x face. So it's perpendicular to the x direction. So we have the negative x face here, the positive x face here. And so it's on a positive x face going in a positive y direction. And so v sub xy as drawn here would be positive. Positive face, positive direction. If it's on a negative face, it would be going in a negative direction to give a positive number. If it's positive face, negative direction, it's negative, or negative face, positive direction, it would be negative. Moment due to torsion or flexure is positive based on the right-hand rule on a positive face. In this case, you see how we've drawn it here. We have a moment on the left. That would be the negative face. And so it has to change direction from the positive moment, which is on the positive face here. Okay. And so one way to think of it, a beam is a positive moment or positive bending if it basically sags in the middle and makes a big smile. Now, obviously, that's going to change as we go to cantilevers and other types of structures. So we get into it in more detail. So quite often what I do with my class problems is I break them down into components so that you can watch them in bits, much like I do with the lectures. So doing the free body diagram shown in this link, coming up with the reaction, solving for the reaction shown in this link, and looking at internal forces at C, which is the ultimate finality of the review on statics. Internal forces at C, shown at this link here, and it should reinforce everything that we've done to date. So go through that, take the time to go through it in some detail. It's sufficiently complicated that most of the issues that you're going to deal with are dealt with in this example. So good luck with that. And finally, one more just to sink it home, dealing with a fixed end cantilever with a point load and a uniformly distributed load over half. And again, I provided the link where you can go through it here, start to finish, starting to happen a little bit faster at this point. And that's it. That's where we needed to get to at the end of the day. Like I say, we missed out in about 5 or 10 minutes, just got off a little slow. So that is the review on statics. Once you're done this, gone through those problems, the whole first assignment is simply to reinforce the review component. So you have everything you need to get through to the end of the first assignment. And now we're into the axial loads, which starts in week 2. So go through the lectures, show up, of course, Monday morning when we show up, it's going to be tutorial time. You'll have opportunity to ask any questions on problems that you're trying to do with statics or anything else associated with the course. So hopefully that was helpful, and we'll see you on Monday morning.